In this session, I want to demonstrate a strategy for solving optimization problems that is different from what is traditionally done in calculus and business calculus. This strategy is Excel-friendly and gives students a good understanding of the objective function for an application. It can be applied to almost any optimization problem, but it excels at optimization problems arising from real applications. Here is a typical application from a textbook. In this application, we want to minimize the cost of constructing a rectangular pasture where fencing is needed along three sides of the pasture. Every single one of us has done this problem, and we understand the point of the problem. Because we understand the mathematics, constructing the objective function is fairly straightforward. However, our students are not nearly so savvy. When faced with a problem like this, their minds tend to wander to somewhat tangential questions like, what kind of animal might stay in this pasture? Wouldn't they just swim the river? Of course, it couldn't be cows. After all, cows can swim. Or maybe sheep? Sheep are actually such accomplished swimmers that there are sheep Speedo swimsuits. If not cows or sheep, maybe pigs would stay in this pasture. As you can see here, pigs just don't have a huge fear of water. And don't think puny little fences are going to keep pigs in the pasture. They can jump too. Let's disregard these minor difficulties and look at a new strategy for finding the objective function for problems of this type. Here is another typical application from calculus. In this problem, we want to construct an enclosure for these jumping pigs that encloses 400 square feet. The fence costs $1.10 per foot around the outside of the enclosure and 60 cents per foot for the divider. What overall dimensions should the enclosure have to minimize the cost of fencing? Let's start with some possible dimensions and evaluate the cost of fencing for those dimensions. In this case, let's start with an enclosure that is 5 feet wide and 80 feet long to give an area of 400 square feet. The key is to make a diagram of this enclosure with each section of the fence labeled with its length and cost per length. This is useful since it helps us to see that the cost is obtained by multiplying the cost per linear foot times the number of linear feet. The cost of the width components is 1.10 times 2 times 5. The 2 comes from the fact that there are 2 width components that cost $1.10 per foot. The cost of the length components come from the 2 80-foot sections costing $1.10 per foot and the single 80-foot divider costing 60 cents per foot. Putting these components together gives the total cost of fencing for this enclosure $235. Another possible solution is an enclosure that is 10 by 40 feet. Working out the cost of the width and the length components gives a total cost of $134. This is a lower cost than the previous enclosure, which is good, but we don't know if these dimensions minimize the costs. These two examples help us to establish the patterns in the objective function for this problem. List those results in a table with the width, length, the cost of the width, the cost of the length, and the total cost. This table can be on paper or in Excel. Continue to add different size enclosures. Note that as the width increases, the length decreases to ensure that the area is equal to 400 square feet. It appears that the total cost is at a minimum for an enclosure that is about 20 by 20. Examining the columns, we see that we can write the length in terms of the width W as 400 divided by W. The cost of the width components is 1.10 times 2 times W. The cost of the length components are 1.10 times 2 times 400 over W plus 0.60 times 400 over W. If we add the expressions for the width components and the length components, we get the objective function. The table helps us to recognize the patterns in the objective function. The total cost can be simplified to yield 2.20 W plus 1,120 times W to the negative 1 power. Next, we find the derivative and locate the critical numbers by setting the derivative equal to 0. This leads to a single realistic critical number at approximately 22.56. The first derivative test indicates that the critical number corresponds to a relative minimum. The graph of the total cost function verifies that at a width of about 22.56 and a length of 400 divided by 22.56, these lead to a minimum cost of about $99.28. This matches what we saw in the table too. Not only does the table help us to write out the objective function, it also helps us to verify the correct solution makes sense. Let's try this approach on a more realistic application. Different airlines constrain the linear dimensions of carry-on baggage. Assuming a bag shaped like a rectangular solid with square ends, what is the largest volume bag whose linear dimensions are 45 inches? We'll start with several bags and calculate their volume. A bag that is 5 by 5 by 35 inches has a volume of 875 cubic inches. A bag that is 10 inches by 10 inches by 25 inches has a volume of 2,500 cubic inches. These two examples are entered into a table with column titles width, height, length, and the corresponding volume. We can continue to increase the width and height to get the corresponding length and volume. Notice that a bag of 15 by 15 by 15 leads to the highest volume in the table. But is this the maximum volume overall? Let W represent the width of the bag. Since the ends are square, the height is also W. To have linear dimensions equal to 45, the length must be 45 subtract W subtract W. The volume is the product of these dimensions. This product is valid as long as the width is in the closed interval 0 to 22.5. Simplify the volume function to yield 45W squared subtract 2 times W cubed. The derivative is 90W subtract 6 times W squared, putting the critical numbers at 0 and 15. Evaluating the volume function at the endpoints in the critical numbers, we see that a width of 15 yields the maximum volume. So the dimensions of the bag are 15 inches by 15 inches by 15 inches. The power of this strategy really shows when developing more complicated objective functions. Suppose the annual demand for wine at a wine shop is 900 bottles. It costs $1 to store 1 bottle of wine for 1 year, and it costs $5 to place an order for wine. How many bottles of wine should be ordered in each order to satisfy the demand and to minimize costs? We'll need to take into consideration the two different costs in this problem, the reordering cost and the storage cost. We'll assume that each order will have Q bottles of wine in it. Now let's look at some specific examples. We could order all 900 bottles in one single order. The reordering cost would be $5, and the storage cost would be the average inventory of 450 bottles times the cost to store for 1 year. This leads to an actual cost of 5 plus 450, or $455. An order size of 450 leads to reordering cost of 2 times 5, since 2 orders need to be made, and storage cost of 225. This leads to a total cost of $235. Let's put these values into a table with the order size, reorder cost, storage cost, and the corresponding total cost. Notice that as the order size drops, the reordering cost increases and the storage cost drops. If each order contains 225 bottles, the 4 orders cost $20 to order, and an average of 112.5 bottles are stored throughout the year, yielding a total cost of $132.50. We can continue to reduce the order size to see the total cost continuing to drop. However, for very small orders, the total cost begins to creep up. For an order size of Q, the reordering cost is 900 divided by Q times 5, and the storage cost is Q divided by 2 times 1. The sum of these costs is the total cost. This can be simplified to yield the total cost function, 4,500 times Q to the negative 1 power, plus 1/2 times Q. Set the derivative equal to 0 to give a realistic critical number of approximately 94.87. The second derivative can be used to determine whether the critical number is a relative maximum or minimum. Since the derivative is positive at the critical number, it is also a relative minimum. However, distributors do not appreciate order sizes with decimal amounts. Realistically, we order either 94 or 95 bottles in each order. If we evaluate these order amounts in the total cost function, we see that an order size of 95 is cheapest. A graph of the function verifies these numbers. A similar problem is deciding how many items should be manufactured in batches to minimize the total cost of production. In this case, we are manufacturing 100,000 lamps annually. There are several costs to consider. There is a fixed cost of $500 to set up the factory to produce a batch of lamps. Each lamp costs $25 to make and $1 to store for a year. We'll proceed as before and let Q represent the number of lamps in each batch. As a first example, let's find the cost to produce all 100,000 lamps in a single batch. The total cost consists of 3 terms. It costs $500 to set up the single batch, 100,000 times 25 to produce the lamps, and 50,000 times 1 to store an average of 50,000 units for a year. This gives a total cost of $2,550,500. Producing 50,000 lamps in 2 batches costs $2,526,000. And 10,000 lamps in 10 batches cost $2,510,000. As you can see from the table, as batch size is decreased, the variable costs do not change. However, the fixed costs increase as the plant has to be set up more often and the storage costs decrease. Decrease the size of the batch so that the pattern becomes obvious. and we can write the cost in terms of the size of the batch Q. The fixed costs are 100,000 divided by Q times 500. The storage costs are Q divided by 2 times 1, and the variable costs are fixed at 100,000 times 25 as the batch size varies. The sum of these costs are the total cost. It can be simplified to give 50 million times Q to the negative 1 plus 2,500,000 plus 1/2 times Q. As with all of these optimization problems, we take the derivative to find any critical numbers. For this function, the only realistic critical number is a batch size of 10,000. We'll use the second derivative to decide if the critical number is a relative maximum or minimum. The second derivative is positive at the critical number, so it is a relative minimum. At this relative minimum, the total cost is $2,510,000. In each of these examples, I've followed the same basic strategy to get the optimization model. Utilizing the concrete values and a table helps students to spot relationships between the variables and to see patterns that establish the objective function. With a large enough table, they can even estimate the optimum value even before doing any calculus. If you'd like to see more information on this and other projects, check out my website, pblpathways.com. You'll find a video of this presentation as well as student projects that you can use in college algebra, finite math, and calculus.